So prior to this, she got her bachelor's, master's, and PhD from MIT with a break to work in the business industry in between. And then subsequently, she was a researcher at Brown. She was faculty at MIT and then also served as director of the Carnegie Department of Terrestrial Magnetism, which is now known as Earth and Planets, and also for ASU's School of Earth and Space Exploration. She has a bunch of additional really exciting roles as well. I'll just highlight one additional one, which is that she wrote a memoir last year, and she has a lot of experience and fun research topics that she'll be able to talk with you all about, potentially at happy hour this evening, if you're able to join us. And with that, I'll pass it to Lindy. So thank you very much for joining us.
Thank you so much for the introduction. Is the microphone working? Is it good? Okay, cool. Thank you very much. No, it's great to be here. I really appreciate it. And thanks for coming out with so much weather drama going on. I know some of you still don't have electricity, so hopefully the hot coffee and makes it feel a little more normal again. All right, so I want to talk about Psyche mission, which has taken over my life for the last 12 years. And I'll talk about the science and how it came to be. And then I'll show you some space hardware pictures, which I think a lot of us like to geek out looking at space hardware. That's always fun. All right, so this is an artist's interpretation of what the surface of Psyche might look like. So I'm going to repeat this a number of times. We don't know what it looks like, so don't be confused by the fact that we have pretty art, because it's just imaginary. Let's see. It's not, maybe we clicked away from the presentation and to Zoom. I think that might be what happened. There we go. All right. So this is just a little reminder that that we as a species have sent humans and also robotic explorers to rocky bodies like the moon. And in case you're not like a moon aficionado, this is the Orientale impact basin, which is on the limb of the moon, and you can't see it from the Earth. You can only, this was a Ranger photo from back in the day. And so I always joke that people should have a favorite lunar basin, and I recommend Orientale. It's a particularly nice one. So we've been out to look at rocky bodies, and here's Burns Cliff on Mars, named after the petrologist Roger Burns. He's a lovely human being. Bodies that are made of ice and gas, like Jupiter, obviously this is Jupiter, and icy moons, like this is one of our favorites. But what we've never yet done is gone to a body that we think has a mostly metal surface. That's what we think Psyche is. And the reason that it's so interesting, it makes it a new kind of exploration, a whole new category of body to go look at, if indeed our ground-based data is correct. And it reminds me of, back in the day, just only a couple of 100 years ago, when people had not yet set foot on Antarctica, and we were still finding new continents, like whole new places to visit. And so Psyche represents this whole new class of objects that I hope will fill in some very interesting information about the formation of planets. So this is also art by our talented guy, Peter Rubin, who's he's a Hollywood sci-fi movie animator. It was very fun to work with him on all the art for the proposal. We Zoomed every Sunday afternoon for a couple of years while I tried to tell him all the science that we knew so that he could try to interpret it in a way that would be as scientifically correct as we knew, but with his twist. And he's done lots of interesting things in his life. Like he designed one of the S's for Superman. And if you are into Superman, you know there's more than one S for Superman. And he's very proud that his was one of the ones that was copyrighted. And so this is one of the fun things you get to do on a big NASA mission, is work with a guy like Peter. And so what does it actually look like? Since I've already made clear that that is not what it actually looks like. This is what it actually looks like. This is what it looks like from my backyard, actually, but it's not that much different in the 60-inch at Mount Wilson, and in Hubble, it's just a couple of pixels. And we are getting JWST data this spring, though, in cycle 1. And it'll be infrared, so that'll be interesting. So just yet another reminder that we don't know what it looks like, and we don't really know what we're going to find. And that's quite different than most space explorations that are designed and sent. Usually there's existing data that we could be improving on, and here it's really, we don't know. And so the other thing that I always say, and that I continue to mean from the bottom of my heart, is that probably all the science that I present to you today, our ideas, are wrong, and that we're going to be discovering something quite surprising and different when we get there. So so don't mistake me as sounding like I'm sure that I know what it is, because I absolutely don't. These are the shape models that we've got. There's actually a couple more in addition to this. Shepard's Mike Shepard 2017, and then Foray, and then Shepard 2021. And you can see that it's not a sphere. I say it's potato shaped because that encompasses any possible shape. And this nice paper in 2021, it's a really great paper. But this figure kind of indicates that maybe we're converging, but really it's only showing two models. And there are other models that are actually quite a bit different than this. So it's been an interesting challenge for the proximity ops team and the trajectory team to figure out how exactly we're going to get into orbit around a body whose shape we don't know and whose gravity field we don't know. But we have some data, and this is what we start with. And so just to remind you about size is also, here's Vesta that Dawn mission went to, and this is how big Psyche is approximately. And then there's Eros, and there is another asteroid on this picture, if you can see it. It's right there, that's Bennu. And so these are the relative sizes. And I find this very helpful to remind myself from time to time that trying to do proximity ops at Bennu is very, very different from doing it at Psyche or Vesta, where no matter how small those gravity fields might be compared to the Earth, they're still much bigger than Bennu's. So we won't have to do that amazing square orbit that OSIRIS-REx was doing around Bennu. And also that Eros and Bennu represent undifferentiated primitive material from the beginning of the solar system that never melted and differentiated into a metal core and rocky exterior. Whereas we believe that Vesta definitely, we think, did that differentiation, and we're pretty sure that Psyche did, but we're not certain. So these are maybe different stages of planetary formation as well. This is how it is, how big it is compared to Texas. I always like to show compared to where we are. It's about the width of the state of Massachusetts if you don't include Cape Cod. So that's another measure. And if we dropped it on Arizona, which is of course a map I show often, it would more or less fill the space between Phoenix and Flagstaff. So as asteroids go, that's quite large for what it's worth. Now, what do we think that it is? Well, let's start with a little bit of data. This was from a summary that we put together with the science team in 2020. The fundamental shape model is known sufficiently well to have an effective volume, agreeing with about 10% of the most recent three estimates at their central values, and within about 30% difference at their 1 sigma errors. So the effective diameter, if you made the potato into a sphere, is about 225 kilometers. Now, why do I find it important to talk about these error bounds? Because the number one indicator, and there are other ones, but the primary beginning indicator of what it's made of is its density. And the way we get its density is dividing its mass by its volume. So if we only know volume by plus or minus 10 or 30%, depending on how many sigmas you're believing in your given day, that means we don't really know the density that well either. And so there's wiggle room on what it ends up being, even from our ground-based data. That's the point of this. So here's a graph I made. I really enjoy graphs that are some quantity, in this case, the bulk density of Psyche versus time of year of publication, because it really shows how people's thinking changes and how our data changes. So look at this point at 11,000 kilograms per cubic meter. And for anybody who thinks about planetary materials, there's pretty much nothing that would be 11,000 kilograms per cubic meter. I've got to go back and see what they thought it was, because I mean, I think that now if we got a value like that, we would know that we just had wrong data, because it's not a teaspoon of a neutron star, you know, whatever the correct amount would be. And so you can see that the numbers are kind of converging, and it was around here that we are writing our proposals. And then since then, the data's really converged. And that's also the miracle of funding. As soon as a mission is funded, people get a lot more interested in making predictions and making measurements, because they're actually going to be testable instead of just sitting out there in the ether forever. And so you see that I've got 3 horizontal lines here too. Anstatite, just representing a typical silicate, a rock material that could be present on this body. Troilite, which is iron sulfide, also commonly associated with the core forming processes on little planetesimals, and camosite, which is one of the typical iron nickel crystals that form in iron meteorites that are pieces of cores. So if it was pure core material, it should have a density around 7,000 kilograms per cubic meter. And if it was pure rocky material, it might be around 3,000. Our team's best estimate right now is here. So we think it's about 4,000 kilograms per cubic meter in bulk density, which would indicate it's a mixture of metal and non-metal. And that's almost the best information we've got right now. It's a mixture of metal and non-metal. But note that most asteroids plot in this little gray box here in the bottom right corner. And because there's a lot of pore space in asteroids, most asteroids are rubble piles. So they're really a mixture of rock, metal, and void. And that gives them a low, or ice, obviously ice also, down at 1,000 kilograms per cubic meter. As of the writing last year, I think Psyche is thought to be perhaps the densest known asteroid, but Cleopatra might be denser, but it's like number 1 or number 2. So it's about as dense as you get in the planet forming area. So that makes it interesting from a compositional point of view. So what other data do we have? So we think that its bulk density is, say, between 3,700 and 4,200, which would predict that it's between about 25 and 60 volume percent metal. But if you think that metal can support more pore space, more void space, it actually could be 100% metal. It could be void plus metal. And so we don't really know. We don't have a good constraint on how much metal there is. But the radar albedo and the reflectance and optical properties all indicate, although non-uniquely, that the body is largely metallic on its surface. And the latest data shows maybe fine-grained metals, which we think, you know, what do you think about a metal regolith is an interesting idea. And we think the way that would be formed would be by impacts, micrometeorite impacts, making tiny, tiny microtectites out of metal. Because it turns out that solar wind radiation does not break up grains of metal the way it breaks up grains of silicate. That's some work by John Krista that'll be published soon. The spectra, this is very interesting. How many of you are petrologists of some variety and you think about the composition of rocks on an atomic scale? Just okay, good. I just want to like not be condescending or like just say the right level of thing. So if you pick up a rock on Earth, a lot of the minerals have a crystal site that will accommodate either iron or magnesium. And on Earth, it's always a mixture of iron and magnesium in there. And that would be a iron oxide or magnesium oxide, not the metal phase, just in the rock phase. But the spectra from Psyche indicate a very low iron oxide in the non-metal portion. So whatever it is that's not rock, like for example, if it is that mineral enstatite, it would be the pure magnesium end member almost no iron oxide in there. So then you have a kind of a chemical question, which is how can you make something where virtually every atom of metal was put into the metal phase, an atom of iron was put into the metal phase, leaving almost no iron in the rock phase. And it sets up a very interesting question about process, which we have no answer for right now. So the second major component after iron, nickel, metal might be a low iron, low calcium pyroxene. That's people's best guess. So that's a pretty weird rock. It's not totally clear how you'd make that. It might not be silicate rocks at all. It could be metal plus, we don't know. So here's a paper that's coming out. I think I just came out online, actually. It's a work by a graduate student, Stephen Dibb, who's being advised by Jim Bell at ASU, who just recently graduated. And he did a really nice statistical combination of likely rock forming materials like iron, nickel, metal, or these enstatite minerals or something like that, and compared them to the spectra that people have taken of the asteroid. And so the little guide up at the top, right up here, these are the different people who've taken the spectra of Psyche. And then those are labeled down here on the left-hand side. And on the right-hand side are the spectra of the minerals that we're trying to match them with. And so the very best matches for Psyche spectra are iron meteorite powder, iron sulfide powder, which is troilite, pentlandite. And so these are all sort of metallic iron meteorite kind of minerals. But then very weird kind of meteorite called a CB chondrite. Does that mean anything to anybody here? CB chondrite? A little bit, couple people. So chondrite in general, so don't you think that the jargon that people who study meteorites, this jargon is just to keep the riffraff out, right? It's to alienate the rest of us. So the word chondrite just means its parent body never melted and formed a metal core and a silicate exterior. It still has its metal and its silicate intimately mixed like it was originally formed around the young star. And a CB chondrite is a very strange kind of chondrite, which I'll show you some pictures of. They're very rare. Nobody really understands how they're formed. And it's just truly bizarre that that's the best meteorite match for Psyche. It just completely piques my interest, and it's bizarre. This is a comment about one of our instruments and how it's going to help us figure out what Psyche is. This is, we are flying a neutron spectrometer that's going to measure the energy of the neutrons coming off the surface of Psyche that have been generated by cosmic ray strikes onto the surface. And the people who do this divide the neutrons into energy categories. So slow neutrons on the horizontal axis and slightly faster, more energetic neutrons on the vertical axis. And you can see here the way they've plotted it, increasing metal is going up diagonally along this arrow here. You can see 20% metal, 50, 80% metal. Increasing nickel goes down vertically, which is why this is now a grid. So each of these vertical lines is less and less nickel. The reason I'm kind of taking you through that structure is because I want to point out that over here, this is the whole range of the lunar surface right here. That's as big as it got on the moon. And so we're expecting Psyche to be producing a huge amount of neutrons that we'll actually be able to plot into this grid and help us figure out how much nickel and how much metal is there. So that's one of the kind of tricks up the sleeve we have to try to figure out how much of Psyche is metal once we're in orbit around Psyche. These are pictures of these CB chondrites. Now look at this one, Gujba. They're all named after, by the way, if you didn't know this, meteorites are always named after the place where they landed. So these are the names of towns, in case you were thinking they had further meaning. So really the names are ridiculous. I'm just gonna put that out there. So the pale gray things, like the thing my pointer is on right now, those are blobs of iron nickel metal. But look how they're largely circular. I mean, these were melted and formed their body of least surface area. They were formed into spheres. And then in between them is this darker gray material, which is in fact silicate material like rock, and has almost no iron oxide in it. And so how in the world was this formed? One of the leading hypotheses for forming these CB chondrites, both of these guys and the rest of the very small family, is that they're kind of the frothy splash of a large impact onto an early forming planetesimal, a little tiny body early in the solar system. So there was metal in the impact and rock, and because of the temperatures, it would have been highly reducing, and the iron would have been driven into the metal phase and out of the silicate phase, and everything would be like a circular blob because it was melted and then frozen together again. So like meteorite froth. It's not a bad idea. It fits the chemistry, but is it possible to make a piece of impact froth the size of Psyche? I'm not convinced that makes any sense. And so that just makes it even more confusing why the CB chondrites are the best match for Psyche. So I just think it's a great story how the data is kind of contradictory and confusing, and it's not just like, oh, it's something obvious that we know what it is, which back when the density was thought to be very high, we thought we did know what it was. And what we thought that it was the core of a planetesimal. So over here, you've got on the left, this is how our solar system started, with a disk of dust and gas that formed into little pebbles. And those first little pebbles are the ones that we get the age of our solar system from. And when I was teaching planetary science, I think Mark knows this, I used to tell the students that if they didn't remember 4.568 billion years ago, they would fail. That was the one thing they had to memorize. That's the age of the earliest known pebble that we found in a meteorite 4.568 billion years ago. So they very quickly formed up into planetesimals. So these are bodies the size of like cities or continents that were like miniature planets that then, and there's a very interesting physics story about how we think they formed. It's not at all obvious. And then they collided together and formed into things called planetary embryos and continued to collide until they became planets. You'll see over here on the planetesimals, I'm showing some that almost look like onions. And in fact, that's what it's called, an onion skin model, where they were warmer on the inside from radiogenic heating, but they never melted. Maybe they had a little hotter in the middle, a little cooler on the outside, but some of them actually melted, which is this red melt, and all of the metal sank to the middle and formed a core. So that's the process of differentiation. Decades ago, people used to be taught that that only happened on the Earth, for example, long after the Earth was its current size. And then there was this miraculous thing called the iron catastrophe, where gee, some of you remember this? Like I remember seeing this in textbooks, not that old. And the metal would all flood down to the center of the Earth and form the core. But now we know that the cores formed originally within just a few 100,000 years of the very first pebbles, like super short, way less than 1 million years. All these cores are forming and then merging together over and over again. And some of the shrapnel, the leftover of planetary formation and the leftover of these planetesimals over here is what's in the asteroid belt today. So that's why we're so interested in the asteroid belt, one of the reasons, because it is a sort of frozen in time capsule of that time in planetary formation. So now people know, quite astonishingly, that it only took about 5 million years to make Mars. But the last giant impact on the Earth, the one that formed our moon, was about 100 million years after 4.568 billion years ago. So 5 million years is just a flash. And so if the solar system's age is a 24-hour day, Mars was made in 94 seconds. And the planetesimals, like what we think Psyche is, were often made in just about 10 seconds of that 24-hour day. So they're very, very old. And so what we think Psyche is, this is what we call our fiducial hypothesis. This seems to be the most likely possibility, that it's a differentiated planetesimal that got smashed 1 to say 10 times, that knocked off a lot of the rocky exterior, leaving the metal core exposed. And if there was a nice big liquid metal core, it likely formed a magnetic dynamo. I always show magnetism lines in purple. I encourage you to make all your magnetic lines purple. And we think maybe it froze from the outside in. You can see that dark frozen lid on the outside. There's actually meteorite evidence that some of these metallic parent bodies froze from the outside in. And sometimes for us that seems shocking because our Earth's core is freezing from the inside out. But remember, it's a completely different pressure regime for the Earth and for these guys. And so what I'm showing here, and this is more Peter Rubin work with me, these yellow volcanoes are sulfur-rich volcanoes. It turns out that if you take the typical mixture of elements that seem to have gone into a planetesimal core, as soon as that starts to freeze, it's the iron and nickel that freezes out first, sulfur gets enriched in the remaining liquid and almost immediately forms an immiscible liquid. So think like vinegar and water. And so the sulfur-rich part ends up being about half sulfur, half iron, which is the stoichiometric formula for troilite, that mineral that I've mentioned already, so iron sulfide. So we would be having iron sulfide volcanoes out the cracks in the solidifying metal shell. And very importantly, the shell would be cooling through what's called its Curie point and able to record that magnetic field before the dynamo goes away. So this is we have this hope that we might find on Psyche pieces of metal that are still magnetized from the original magnetic field. It won't have a dynamo anymore. That'll have died long ago. It'll be totally solid. It'll be all cold. It will not be a surprise like Pluto. It's going to be cold and totally solid, but maybe it'll have remnant magnetization in it. And maybe it'll have evidence of troilite, sulfur-rich kind of volcanism on the surface. So that's our wild guess kind of model. And what it would look like now is there would only be parts that would be magnetized. So it wouldn't have that beautiful dipole field. It would have a field that the spacecraft could fly in and out of as we orbit the body. And so that's what we'll be looking at from a magnetics kind of point of view. Very important to remind you, almost certainly completely wrong. It's just our best guess. And amazingly, it turns out that, and don't look at this yet, because I want to tell you a slightly different story first. I should have left a blank slide in there. Eric Asfog runs all at University of Arizona, runs all these models of solar system formation and keeps track of these bodies. And looking for ones that have a kind of largely metal surface, very dense planetesimal after planet formation. Very often it doesn't happen, there's none. Every once in a while there's one and sometimes two. And so Psyche is a very unusual object. And so even our most likely hypothesis of how it formed is an unlikely hypothesis. And so I ask you to put on your philosopher hat and think about, what does it mean to make an Occam's razor, most likely simplest idea for how something happened if that thing is an extreme outlier and you can't really rely on a bell curve population of items to choose the simplest process for? I think it's really interesting scientifically to think about that. So remember how chondrite for a meteorite means that it has never differentiated into a core. Achondrite means it did. So this is one possible way you could make the Psyche that we see. Something melted and differentiated like this into its mantle and its core, and then it froze, and it would have very low iron oxide rock near its core and higher iron oxide rock near the surface for mineralogical reasons that I'm not going to pedantically recite to you right now. But then if it had a bunch of impacts, it could strip out the higher iron rock and leave behind low iron oxide silicate rock and metal. And so maybe that's what it is. That's our best hypothesis. Or it could be what's called a palissitic core mantle boundary, where at the core mantle boundary, there was a mixture of rock and metal. Or maybe a CB chondrite. Maybe it's that. So those are all speculative. And then alternatively, it actually could be chondritic. Maybe it never formed a core, but maybe it formed somewhere in the solar system where the conditions were highly reducing. And so it has a lot more metal mixed with its rock, even though it never melted. So it could be high iron metal and low iron rock, never melted. So that's our alternative. We don't have any examples of that material, but it's theoretically possible. So we're out on the ragged edge of things that we might think. And any of these could have been made into rubble piles. So that's where you get that void space question. All right, so that's what we think it could be. Now, where is it? It's in the outer main asteroid belt, often closer to Jupiter than it is to the Earth. It's very, very far away. Have any of you guys seen these fabulous hyperbolic headlines about how Psyche has enough metal in it to make us all billionaires? We have so many headlines. I have a Google alert, you know, when NASA's Psyche mission comes up. And it happens almost every day somewhere in the world. Someone is writing a headline about how this asteroid is going to make us all rich. And indeed, if it was possible to tow it back and sell it on the metals market, everything I just said, absolutely impossible, and not crash the price of metal by doing it, by flooding the market, also impossible. It would be worth some multiple of the global economic product. I mean, it's really, really valuable from that point of view. But because everything I just said is impossible, it's never, ever going to happen. And also, it's really far away. Like bringing it back to anything from there is really impossible. So be sure to laugh at anyone who says that to you. It's a very good thing to do. All right, we've got 3 big science goals. The first one is understand a previously unexplored building block of planet formation. Then to look inside the terrestrial planets, including Earth, by what we hope is directly examining the interior of a differentiated body, something we can never do on Earth or any of the other nice rocky bodies with cores. And then finally, to explore a new type of world, not made of rock or ice, but of metal. We're really curious about what its surface is going to look like. We have 5 science objectives. This is another beautiful Peter Rubin illustration. What might tiny impacts into a rocky and metal surface together look like? I just think it's beautiful, even though probably there's nothing in real life that looks like that. So our first objective is simply that: determine whether Psyche is part of a metal core or if it's unmelted material. And we think that we have got, think about this for a second. Every second sentence I've said is, but we don't know. And imagine trying to design a spacecraft to go to an unknown object to test a very specific hypothesis. It's been really, really interesting to try to reason our way through all of the wavering roads of what this could be. Objective B is to determine the relative ages of surface regions by counting impact craters. We can't promise to get the absolute age of the surface by counting craters because we don't know where Psyche has spent its life. And we don't know what the typical cratering curve is for every part of the asteroid belt, let alone maybe Psyche was formed in the inner solar system and then expelled, a la Bill Baki's idea. But what we can do is compare the cratering rates on different parts of the surface. And for those of you who are not totally keyed into cratering rates all the time, the thing to think about is that the longer that an airless, atmosphere-free surface is exposed to space, the more meteorites are going to hit it and make impact craters. So a very young surface in the solar system has very, very few craters in it. And an old surface has a lot. And so we'll be able to compare how many craters there are in different areas and see if we have newer and older areas. And then C and D are for the geochemical nerds among us. We're going to measure the light elements in the metal phase, which maybe will inform us about what some of the building blocks of our core were. And then we're going to look at the oxidizing or reducing conditions of core formation. Did it form with a lot of free oxygen around or not? And this complicated graph is just a compilation I made a couple of years ago of the most commonly supposed light elements in the Earth's core, silicon, sulfur, oxygen, potassium, and carbon, versus what the Psyche detection limit is, and who thought which elements were going to be in our core. So we'll compare what we measure with what people think is in the Earth's core. And then finally, we're going to characterize its morphology. And one of the questions we have is, what does an impact into metal look like? If we have an all metal surface, which I'm hoping for, one thing that happens in the lab is that those ejecta flaps that in rocky bodies just kind of fall over outside the crater, they can freeze into spikes and vertical flaps if it's metal and small craters. And I think that would make a very interesting surface. And if someday people want to go and mine metal out of near Earth asteroids, it might be nice to know that the surface is going to be wildly prickly with pointy shards of iron metal. And so that could be a possibility. So how does a NASA mission happen? Well, ours started in 2011 with this paper that I wrote with Ben Weiss and Maria Zuber called Chondrites as Samples of Differentiated Planetesimals. So I've just spent this whole half hour explaining how chondrites come from bodies that never differentiated, that they themselves are still intimately mixed metal and rock. They never melted, they never formed a core. So we wrote this paper that suggested that certain chondrites could be the outside shell of bodies that were differentiated on the inside. And maybe you think that this isn't a minutia, we're in a like tiny corner of a final rabbit run of some aspect of science. But as is typical in science, it caused a furor because we were contradicting people who had believed certain things for their careers. And it was a very, very fun moment at the Lunar and Planetary Science Conference when I walked up to give, I was a junior faculty at that time at MIT and like in my second year or something. And a little bit more than that, but I wasn't tenured yet. And I was walking up to give my talk at the podium, and people were already lined up 3 deep at the microphones to rebut me before I even started to speak. And it was good. We had a great conversation, and people didn't think, at least didn't say to our faces, that we were totally nuts. And it's nice when they don't say it to you directly. But then an interesting thing happened, which was a scientist at Jet Propulsion Laboratory emailed me and said, would you be interested in proposing a mission to test your hypothesis? And I had never thought of proposing a mission or leading a mission. So, but that's the kind of email you're like, huh, that's kind of cool. Let's go have a meeting. Let's go to JPL. That'd be fun. So that was 2011. And here we are now, having done all these things. And so we wrote a step 1 proposal. This is Peter's cover art for it. And you can see what we're showing here is one of those impacts that maybe could have stripped the rock off of the metal core of a planetesimal. We're trying to tell the story for the people who are reading our proposals. 28 step 1 proposals went in. These are written by dozens of people over several years. I forget, 240 pages, something like that. And to my astonishment, we were down selected for step 2, which means 5 missions could go on and propose a 1,000-page concept study report that would explain everything about the mission, like the total mission plan. And by the end of this, we had 140 people working on it. And this is maybe 30 seconds later with the impactor screaming off and the metal core being revealed. So we're keep trying to tell the story. And then to my intense surprise, in 2017, we were selected. And so we're the lead at ASU, and our partner is the mission manager, Jet Propulsion Laboratory. And then Maxar has built our what's called the chassis, the middle part of the spacecraft, and the solar electric propulsion system. So that's why I call this an electric journey to a metal world, because we're actually not using chemical propulsion, where it's kind of like the Tesla of space, of spacecraft, that we're running totally off solar power, and our propulsion is actually the noble gas xenon. We ionize atoms of xenon and send them out through little potential fields, and that mission of momentum pushes the spacecraft a tiny bit. And I've even calculated how many moles of xenon per kilometer that we used to get to Psyche, which I forget right now. But we're flying 1,068 kilograms of xenon as our propulsion system. And then we have science instruments from Johns Hopkins. We've got the gamma ray and neutron spectrometers that will give us the composition. And then Malin Space Science System has made our imagers, so we get pictures. And the Danish Technical University has built our magnetometer, so they've been a great partner. And then we'll have a gravity science team as well, because with a lumpy, funny shaped object made of perhaps materials where one is twice as dense as the other, imagine how bizarre a gravity field might be. So we'll start far away measuring the gravity field and step down as we can find stable orbits, which I'll show you in a minute. So here's the size of the spacecraft. It's quite big. And the solar arrays are just over here on the right. They're shown folded up against the side in their launch configuration. So we've got our gamma ray spectrometer up at the end of a boom to keep it away from interference by the material of the spacecraft. The neutron spectrometers here. This is our beautiful high gain antenna. I just learned recently that the power of these radio antennas is so high that we can't turn on a high gain antenna until we're like a half an astronomical unit away from the Earth, because we would both damage the deep space network coming in, and the deep space network would damage the spacecraft going out. So we have to use low gain antennas. And so it really kind of blew my mind. Like, there's a lot of power. It's a very severe danger to humans if these get turned on accidentally while it's on the ground. And so there's a lot of fail safe about that, because it would burn you. And then there's, this is a really cool thing, DSOC, the Deep Space Optical Comm. That's a tech demo that we're flying for the crewed spaceflight side of NASA to test communications by laser instead of by radio. And we'll be using it when we're at about the distance of Mars. The joke is that this is how we're going to do Netflix to Mars, because you can pack a lot more data into a laser than into a radio. And I can tell you more about that if you're interested. I don't want to take up more time right this minute, but it's a very nerdy, fabulous, cool thing. And then the cameras are here, 2 of them, the imagers, and the magnetometers are up in a boom in what's called a gradiometer configuration, because we can measure the magnetic field here and here, and that allows us to subtract out the magnetic field of the spacecraft. And then these are the little ion thrusters that use xenon to get us going. And this is how big it is with its beautiful solar arrays unfolded, which we'll do right after launch. Almost 25 meters. It's the size of a single tennis court. And at Earth, this is 20 kilowatts of solar power. And then because solar flux goes down as 1/r squared, by the time we're out at Psyche at about 3.2 AU, we have only about 1/10 the power that we have at Earth, but it's enough to do everything for the spacecraft. So that's just gives you like a little insight into the crazy design configuration that's needed to make a spacecraft that runs. We're going to launch on a SpaceX Falcon Heavy, and we're going to re-land the boosters. And I got to sit on console in mission control for a SpaceX launch of Falcon Heavy with landed boosters in the beginning of November of last year. And it was just incredibly fun. And the sonic boom of those boosters coming back down was the loudest I've ever heard in my life. And even though I knew it was happening, I was watching it with my eyes standing outside the parking lot. And as soon as it finished launching, everyone ran out of mission control into the parking lot to see it with their eyes. I still gave a little shriek when the sonic boom came because it was so loud. So I encourage you to come down and watch. It's gonna be super fun. But wait, okay. Last year we were supposed to launch in August. That was the plan all along. By June of last year, we knew that we couldn't accomplish the 2022 launch. And I don't think I can really adequately convey how traumatic that is to the team. We actually had created a miracle by building the spacecraft through COVID. COVID hit really in March of 2020, and our critical design review was in May of 2020, meaning that we passed CDR. That's when we start really building in earnest. It was the first remote review that NASA had ever run. And we got permission to go forward, and we somehow had to build the spacecraft as remote as possible. You can't build it all, you have to have people there. JPL was completely closed for several months. No one could be on lab at all. So, and we didn't have several months of margin in our couple of years build plan. And so and people were sick and their families were sick and people were dying. We were all there, right? Remember how hard that was. And we did not give up, and we fixed hardware problem after hardware problem. Because you can imagine the subcontractors and the sub-subcontractors are having all the same problems that all of us are having, but they don't have the urgency and the vision and the need to launch at a specific time. So we're getting parts that are wrong and parts that are late and testing and finding mistakes. We actually completely built the whole spacecraft, completely working, and sent it to Kennedy. And the thing that stopped us was our software. We just were not finished with the software and the software test beds. And the whole team, everyone's working extra time and they're super stressed and they're just like driving to make it. And when you've got that level of commitment and momentum, putting the brakes on and saying, no, we're not. I mean, it really is a kick in the stomach kind of feeling. It's very, very hard. And then what happens is NASA sets up an internal review board to figure out what happened and can we launch next time. Now, this is not a launch into low Earth orbit where you can launch lots and lots of times. These planetary launches, you know, Psyche's way out there. It's sometimes in a completely wrong part around going around the sun for us to get there. There are whole years where it doesn't make sense to launch for Psyche. So we really only have very select moments. And so the review board was there to say, can they make their next opportunity? Should we let them or should we cancel them? So from July through October, we all had more or less 3 full-time jobs, talking to the review board all the time, telling them everything that had happened, helping them interview everyone on the team that was relevant, then also rebudgeting and replanning the whole mission and finding the next launch opportunity, and then also continuing to finish the spacecraft. So last year was the most stressful professional year of my life, and I very, very much hope I never reach that pitch of stress again. It was hard. The team was amazing, and we've really come through it in a good way. And we had this beautiful thing called a continuation termination review, where I and parts of the team flew to headquarters and sat with 90 people while they debated our fate for several hours and then voted, continue or terminate. And so it's hard to go through that. But the team really did a good job, and the board did a good job. They were very helpful, very insightful, really helped us tease out why it was a surprise to us that we're not going to make it. Like suddenly, it came upon us suddenly. And so we learned a lot, really, really helpful. The board report is available on nasa.gov if you're interested in reading it. And the 2 big findings they had were around communications and staffing. And so an awful lot of this comes down to team culture, which is something that I've always worked really hard on and worked in, say, 70–80% of the team. You got to have the people who are holding the soldering iron or typing the code able to have their voices heard. You've got to have them sitting at the table and expressing what's really happening, because every layer of management that information flows through, it gets smoothed out and the emotion gets stripped out and the specifics maybe go away and you don't know how bad it is. And so there was one part of the team where that didn't happen. Communications were shut down. So I just think it is so important to welcome every voice. And that's also a force for equity and diversity and valuing people's really purpose. And so it broke my heart that it was a failure of that really caused us to be surprised, failure of communication. And then we had a problem with staffing. JPL just doesn't have enough people to do all the work they need to do. And the couple of really top experts who could have pointed earlier and said, you're in trouble, were not on our project. And so there was kind of combinations of things. But I share this because I feel like these are life lessons in how these things go. All right, so we're going to launch this October. We are going to launch this October. And then what happens, the trajectory here is in purple. We go around and we get a Mars gravity assist in 2026. And then we keep going around and we reach Psyche in 2029. And so one other heartbreaking thing is that our previous trajectory for last year was just 3.4 years. This one's like 6 years. It's the best we could do. There isn't another miracle trajectory for us right now. And so our launch period is October 5th through 25th, and our arrival is August or like mid 2029. We don't know exactly when we're going to arrive yet. So come to the Cape in August. We have a big launch party. You can imagine how big that's going to be. We'll start way up at orbit A, about 700 kilometers altitude, doing imaging and mapping. Once we get there, then we'll step down to orbit B around 300, and then down to orbit C at 190, and then orbit D, our closest one within 1 radius, so we can get the good gamma ray data. So other than the gamma ray data collecting the composition of the surface, all the other instruments will be on all the time. All right. just to say a few more words about the importance of teams, I just think this is so important. Here's a little part of our team. At peak, we are 500-600 people. Right now, we're about 300 people. Overall, we've had almost 2,000 people work on this project, and at organizations all over the country and a few organizations overseas. It's a big project, and trying to make a kind of a united culture has been, of course, a big challenge. And naturally, like the largest part of the team is the Jet Propulsion Laboratory, and I don't work for them. I work for Arizona State. So I've been going to JPL more or less every other week now for a decade, trying to really embed, and it's been helpful to do that. And I think positive team culture is incredibly important. One thing is that there are better decisions made, more ideas are heard, cool heads think better. I've actually had a conversation with a senior aerospace guy who's like, you can't run missions like this. You've got to have people standing up and pounding on the table and screaming at each other, because otherwise you will not get to what they really think and believe. But I believe that when people make their decisions that way, then all the quieter people who don't feel like they've got a cohort are silenced. And that would include all the junior people who actually know what's going on. So I was very, very opposed to that. It reduces project risk for this very reason. We learn more. We have a motto on Psyche mission: the best news is bad news brought early. And it worked over and over and over again, and then it didn't work. Also, attraction and retention of talent. It turns out you need almost 30% of people in a group who you feel like are like you in whatever way you characterize yourself before you don't feel alone anymore. But if you feel alone, and so this is a point that it doesn't matter what your hiring rubric is, if you don't have a positive culture where people can succeed on their merits, you will never have a diverse workforce, because everyone who feels like it's just the people shouting and they don't have any cohort to support them, they'll just cut their losses and go someplace else. And so we see that happening. So this is another reason why culture is so important. Rudeness and bullying and harassment reduce diversity. So I guess that was like the end of my little rant about team culture, but I wrote an article, if you're interested in this stuff, called "Is It Time to Say Goodbye to Our Heroes?" I published it in Issues in Science and Technology, and it's suggesting a kind of a single senior professor owning a mountain of resources model. Not that I think that needs to totally go away, and it can be great. It's gotten us a long way in 1,000 years, but I think that working based on teams, looking at important questions, is a good way to increase diversity and increase the speed of discovery. So that's what that article is about. We have this great student collaboration and public engagement process. We've had over 1,350 undergraduates from 20 universities work with us so far. We've got a capstone program. I think we have 50 capstone teams right now running all across the country. We've got free online courses that are available through our website. We have the Psyche inspired artwork where people apply, students from 2- and 4-year universities, any media, any major, and we pick 16 per year and we fund them to make 4 original works of art. And so it's very fun to look at on the website. There's music, there's film, like everything you could imagine. And then we're very active in social media. These were these cool resin psyches that somebody made this year that I really like. And so let's see the spacecraft in the last few minutes. This is how you ship a spacecraft in a giant shipping container that is made custom for the spacecraft. And it holds the spacecraft from the adapter ring on the base of the spacecraft. It's the same way the spacecraft gets attached to the rocket. It holds it on its side rigidly, and it's completely climate controlled. It's sealed, so it's a clean room inside, and it's instrumented, and it has a generator and a backup generator so that it's absolutely maintained no matter where it goes. And everything gets measured: shock, acceleration, temperature, pressure, particulate matter, for the whole trip. And so these are very expensive. They cost a couple $1 million, several $1 million. And this one, which is Maxar's, has stenciled on its side, "Space hardware do not drop," and which did not actually fill me with assurance that my beautiful spacecraft was safe. I was pretty nervous when it was being shipped from San Francisco down to LA along the coastal highways with the following and other car. And I will just tell you, and there's so many anecdotes you can imagine from this thing. That shipping container of Maxar's does not fit into a C-17, which is the big transport aircraft that NASA offers us to fly the spacecraft from Jet Propulsion Laboratory to Kennedy. It only fits in an Antonov. Antonovs are from the Ukraine, and they're not offered free by NASA. And so we decided we were going to build a shipping container for the spacecraft that fit into a C-17. And we did it together with 2 other missions and made it so it would fit for all the spacecraft. It's made by BAE in Europe. And then we were watching it ship. It's being shipped on a like a big ship. What do you call it? Like a container ship. And like, okay, it's going through the Panama Canal. Okay, it's coming up the coast. It's arrived in California. They've got it on the truck. It's at Marsh Air Force Base. Okay, now it's coming up to JPL. They ran it into a bridge. So what they do for these really careful shipping things is they plot the path and they drive the path and they get the height of every bridge and they do detours around the bridges and they have to get a special permitting process with the police for the whole way. And then when it happens, there's a police car in front and a police car in front, and then a mile ahead there's a pole car. It's a truck that has a pole in its bed, which is literally the height of exactly what you're shipping, because bridges flex. And so the bridges you think you could go under one day, it could be that you can't today. So you drive the pole car to make sure that everything's going to fit. So the pole car knew that the path was, this bridge is known to be too low. So you take the exit and you go over and do this. And then the police came and they just drove straight under the bridge and the container followed them and smashed into the bridge. So now we're like yet another like death moment for the mission potentially. So I and the project manager at JPL get on the phone to the guys at BAE and we're like, you got to put some people on the red eye. We need them here tomorrow to find out if it's breached or if we can use it, or it can be mended. Because if we have to ship it on a truck across the country, we've got to do all the permitting, blah, blah, blah. And he goes, and we said, you won't even believe it. We ran into a bridge. And the guy laughs and he goes, like 20–25% of our shipping containers get run into bridges. So this is like the hidden world of NASA, right? So here it is, arriving at JPL in 2021, being lifted by that hoist. This is the hoist, the top of the hoist here. And this is down onto, this is the body of the spacecraft. And there's the high gain antenna. And these are the booms that the instruments are sitting on. And it's in one of the giant JPL clean room high bays, where you can build gigantic things in a clean room setting. You can see everybody's all gowned up. And that is super fun for me to do, since I'm not a spacecraft engineer, to go and get gowned up. And you go into a little thing like a phone booth. Maybe some of you have done this, called an air shower. So you gown up completely over your face, over your hair, over your shoes and your gloves, and you put on a degaussing strap and you plug it into a ground. So you take all the static electricity out of your clothing, because that's enough to really hurt a spacecraft. So you have to degauss yourself. And then you go into the air shower, this little thing like a phone booth with nozzles of air all over it. And then a big fan at the top sucking the air out. And you do the air shower dance like this until it blows all of the little particles off of you and sucks them away. And then the other door opens and lets you into this place and you can sit with your spacecraft. So this is me and Henry Stone, our project manager with the spacecraft that day. In the clean high bay, we're so excited. This is the Deep Space Optical Comm installation day. There it is being installed, and the team very proud of what they've done. And this was kind of a hero shot for us in August of 2021. Everything that's in red means remove before flight. That's one of the things you learn. And here's the gamma ray spectrometer out here at the end of the boom, and the neutron spectrometer is wrapped up in reflective foil like a pizza box. And then here's the ion thrusters, the Hall thrusters. You can see with the people how big they are. There's 2 on the end of each of 2 arms. And then here's the arm installed on the spacecraft on the left. So that arm can go out and turn so that we can thrust in the direction that we want. And here's what it looks like thrusting in a vacuum chamber. The ions of xenon are blue. So that's actually what it'll look like in space when it's flying, which is kind of cool. Then we prepared for environmental testing. This is a giant carbon fiber tent that the whole spacecraft can go into so we can test its own electrical and magnetic interference. It's a big Faraday cage made of fabric, which is kind of cool. Then we also put it into a thermal vacuum chamber. This square right here is the bottom of the spacecraft, and the yellow is the adapter ring. And this big open space here is the thermal vacuum chamber at Jet Propulsion Laboratory. It's 25 feet in diameter and a giant door. See the person on the left there? There's a person for scale. A door comes and shuts and clamps in space, and then they evacuate the entire inside. And they have these huge lamps at the top that can bring it to 40 times Earth solar power, or much, much less. So you can do all your thermal tests and everything in vacuum. It's an amazing thing to do. I can't even tell you how much liquid nitrogen goes through. Like, they actually have the tankers just lined up continuously to run this thing. It was very impressive. Did that during COVID. Here's us testing that we can deploy our solar panels, beautiful solar panels. And here it is arriving at Kennedy Space Center in that C-17, because our shipping container was okay. And there it's staying until launch. And then finally, this is me on the left, and Brian Bone, our assembly test and launch operations manager, on the right, looking up at the spacecraft, and he's pointing with a flashlight to show me where the comms panel had just been installed. And I welcome you all to follow what's going on our website or on social media. And I'm happy to answer any questions if there's a moment for that. I think I went right a little bit longer than I meant. So thank you very much for coming today. We have time for questions, or we need to let everybody go? Go if you need to, of course. Yeah. Oh, yeah, those are great.
I just have a question about the magnetohydrodynamics inside this, small, bodies. Basically, you're gonna, if you met iron, in there, and it needs to kind of convect or have some sort of, Taylor column for circulation of charges to make a magnetic field.
That's right.
And is it big enough, or is it, to really do that, to generate magnetic field?
Yeah, it did. And Krista will be able to talk about this at huge length. But yes, it seems like the conditions of liquid metal cores in planetesimals were quite conducive to dynamos. And in fact, many iron meteorites that are thought to be parts of these cores that have come to Earth have remnant magnetization, presumably from their parent body. And in some cases, like a large fraction of the power of Earth's field. So it can be significant. Yeah, we'll find out.
Hey, great talk. I had a question because you said that, the reflectance best matches a CD chondrite,
Yeah,
which is weird
so
because
weird.
how do you get an object that big to be a CD chondrite?
Right.
I was wondering, well, if just the surface match a CD chondrite, if you've had billions of years of impactors, meaning the entire surface could be frothed, but the interior could be, remnants of a planetesimal core or something like that.
Yeah, the only challenge I have to that idea is that one of the keys is that all the iron oxide is reduced out of the rock and into the metal. And if you have many small impacts, those are not energetic enough to fully reduce the material that they strike. But everything I just said could be wrong. So, yeah.
I have a question about the spacecraft, everything that goes into it. Does it come back, or do you just rely on the comm to transport back all the data?
It's just the comm. So it's all going to be Deep Space Network, radio comm. And then we'll get, hopefully, if we're successful and everything's good, we'll get an extended mission. And our current plan, if we get an extended mission, is just to cycle down closer and closer to the surface, getting better and better data. But we've had some of our Psyche-inspired art interns find this incredibly depressing, that you work all these years on this spacecraft and you love it so much, and it feels almost like a family member, and it's never coming back. So they actually wrote a children's book, which is available on our website, about how happy the spacecraft is to spend its life with its asteroid.
Yeah, in your beautiful depiction of the whole surface of Psyche, you have what looks like a very impressive scarp. And I'm wondering what the actual speculation is on how strain is accommodated as the body solidifies. Like, is it actually expected to deform prettily like that? Or? It's
totally plausible, and feel free to do better modeling than's been done. but the point of that is that as we showed it freezing from the outside in. So that's first of all an assumption. And as the iron nickel freezes, it contracts. As more and more freezing happens, the first parts to freeze need to shrink, like the shell needs to shrink to accommodate the shrinkage of the interior as it freezes. Does that make sense? And so then you would get like thrust faults in the brittle outside layer that's very cold up against space is a hypothesis.
And Lindy, so I had a question, since this is such a, you sort of don't really know what you're going to, and there's all this uncertainty that you've emphasized. What part of the spacecraft and instrument selection process, sort of addresses that? Or did you,
Yeah. Yeah, the design of the spacecraft has stayed extremely stable since step one. Like we really did our work pre-step one. And we made lots and lots of basically matrices of what are all the possible things that Psyche could be, and what are the individual characteristics that we would see in each case, and then what would we measure with every instrument, and could it be definitive? It's really it's a mind bender to try to get your mind around. And I showed that density figure from the 2020 summary paper, and then there's a 2021 paper that I led also to really talk about that. And there's one of those figures in there, one of those kind of matrices of what might we see and what would it mean about the provenance of Psyche. And I totally welcome you to go and dig into that and critique it, because that would be very helpful.
I was wondering, so you were saying how you don't know what it looks like, you don't have a good idea of what the surface looks like. How do you obtain spectrum data? How are you able to know that kind of information?
Yeah, through telescopes, really. I mean, just what it means is just we look with the telescope at it and we see the light that's shining off it, and then we decompose that light into a spectrum, and those are the spectra that we saw. And an interesting thing is like that first picture when I said this is what Psyche really looks like, and I had the little red circle around the little white spot. So you're just looking at that white spot and recording the light with your telescope. But as Psyche rotates, and so, the Earth's rotation axis is just off vertical, giving us our seasons. Psyche's is more or less in the plane of our orbit, in the ecliptic plane. So I call it like rotisserie chicken mode. And so as Psyche's rotating once every 4 point something hours, and you're looking at the light through the telescope, the light is changing. So we know the surface of it is changing. So it has little different compositions during different like epochs of its thing. And so you look at the spectra and as it changes over time and try to match it up with meteorites. Yeah, I'm very excited to see the James Webb data. That's going to be really great. Yeah, that's a great question. So much complexity, right? 1 million specialists. I don't do that stuff. I don't know how to do it. I can explain it to you like this, but I've never done it. Yeah.
So I guess I'll ask the James Webb question then. So in the infrared spectrum, how is that gonna maybe help differentiating among the spectra you already have?
Yeah, so one thing is how hot or cold does Psyche get and how quickly does it heat or cool off? That helps you with composition. And that's something that Catherine DeClear at Caltech has been doing with the ALMA Observatory. She did a really great paper on that. But the other thing is that the spectra, when you decompose it, and I do it with my finger again, just to say, you run across in the infrared, there's some bands that indicate the presence of water, either water ice or water bound into silicate minerals, like the equivalent of mica. It wouldn't be mica, but something like that. And there's a couple of people who think that they've seen an indication of a hydration feature on Psyche. And so this team really wanted to look for that hydration feature. And so they asked me to be like a participant to kind of advise them on this current state of the art, but it's not my project and they're going to be finding what they need to find. This is, by the way, something some PIs like hold on to the science of their mission and insist that everyone agree and that you come to consensus. And I don't believe in that. I don't think that's how science works. And so I just hope everyone does good work, but they're welcome to disagree. I personally think that if there's a hydration feature on Psyche, it's probably from a later impactor, from some chondritic, undifferentiated material known to have water in it, all that stuff does, that smashes onto the surface, which we know happens all the time, including in the present day. So I think it's very unlikely that there wouldn't be any water on the surface, but I don't think it's part of the story of the formation of Psyche. But I think this new data will help us with that, because what if it's persistent and completely covers the surface? Then we'd have to change our mind a little bit. Yeah.
All right, I think we have to wrap up questions unless you have a very quick one.
I can repeat. Oh, good one.
That it started off with an email following your chondrites as remnants of a differentiated planetesimal. How did you, but now, how did you end up going to Psyche? Is Psyche the only
Yeah, so this is,
have much of a chondrite trust from the
no, probably not, although we'll find out more shortly. So there were only like 4 or 5 of us, Ben Weiss and me and Eric Asfog, like people who were sort of involved in the early thinking, and we'd go out to JPL and brainstorm. Took us about 6 months to decide what our target should be. What we really wanted was to find a family of asteroids that we thought was a recently disrupted, differentiated body. So we could see pieces of crust and pieces of core and pieces of mantle, and that would really help us test. Turns out it's not really clear what families there are besides the Vesta family. There's ideas, but they're not for sure. And the spectra of the ones where people think that there are families that were recently disrupted, so the pieces are relatively close by. The spectra of them are more or less the same, and so they don't seem to have been differentiated bodies. But even beyond that, it turns out it's like impossible to send, it's not, unfortunately, we don't live in Star Wars time. You can't just go out there and like zoom around, look at all the pieces. You know, you're on orbital paths. And so visiting many pieces of a family in the asteroid belt is also almost impossible. And so in the end, we thought, well, here's a place we can go find out about cores and see what kind of rock is near the core. And that's the closest that we're going to be able to come to this. But I would just add, so it might be interesting to some of you might have written something called a science traceability matrix, which is a thing that NASA's way into. I really recommend them for like planning your life. On the left, it's like a giant Excel spreadsheet. On the left, you've got the biggest goals of planetary science, break them down into smaller goals, write your 5 science objectives, explain exactly what you would need to measure in order to test those hypotheses, and then what kind of instrument you need to make those measurements, and keep working right until you end up with a mission design. We went through over 60 versions of this before we ended up with a good version in the end. But the reason I add this story is because we really did write ours from left to right, including figuring out what object we wanted to go to. Mostly they're not written left to right. Mostly people come with an instrument they're determined to fly because it's their instrument that they make, or a body they're determined to go to because it's their favorite body, and then they build out the traceability matrix in both directions from whatever they're starting with. It was really nice to build it properly from a completely blank slate and end up going to Psyche.
Okay, let's thank Lindy again for a
Thank
great
you very much.
presentation.
Thanks for coming.